Welcome to Spaceverse, your portal to cosmic adventures. NASA's Voyager 1 spacecraft left our solar system after 45 years. The results were more startling and puzzling than experts expected. Voyager's extraordinary data, from unexplainable signals to strange phenomena at the border of interstellar space, is challenging everything we thought we knew about the universe. Could these results solve humanity's long-standing cosmic mysteries? This will change your view of our place in the universe, so prepare. NASA launched the Voyager mission in 1977, which became a space exploration legend. Voyager 1 and 2 were designed to study faraway worlds using an unconventional planetary alliance. After a brief mission, these spacecraft have flown to the solar system's edge and beyond for decades. When NASA scientists foresaw an extraordinary alignment of the outer planets from 1977 to 1980, the Voyager missions were conceived in the early 1970s. This alignment every 176 years allows a spaceship to use planet gravitational pull to slingshot between them. This would drastically reduce the time and fuel needed to visit several planets. NASA created two planet-exploring spacecraft to take advantage of this opportunity. The Voyager spacecraft studied Jupiter and Saturn's atmospheres, rings, moons, and magnetic fields. They wanted Voyager 2 to research Neptune and Uranus, if that worked. The two Voyager spacecraft carried 11 scientific instruments to measure plasma waves, cosmic rays, planetary atmospheres, and magnetic fields. Each spaceship also has imaging systems and cameras to obtain close-up photos of the outer planets and their moons. Voyager 2 was launched before 1. Slowing down allowed the spaceship to visit Jupiter, Saturn, Uranus, and Neptune. Gravity helped this long trip by boosting speed without fuel. Voyager 1 aimed to reach Jupiter and Saturn faster. After seeing Saturn, Voyager 1 was placed on a route to leave the solar system faster than Voyager 2, which visited Uranus and Neptune. We only knew what Jupiter and its moons looked like from Pioneer 10 and 11 flybys in the early 1970s and ground-based observatories. Previous expeditions illuminated the Jovian system, but they barely scratched its complexity. The twin Voyager missions were supposed to improve on Pioneer's findings by taking better photographs and researching Jupiter's magnetic field, moons, and atmosphere. However, the Voyager's 1979 encounter with Jupiter astonished scientists and led to a series of revolutionary findings. Before Voyager, astronomers had monitored the Great Red Spot for over 3 centuries. The massive storm may have eaten 3 Earths. But scientists thought it was just a long-lived atmospheric event, like Earth's high-pressure system, and stable. The Voyagers showed that the Great Red Spot is more complex and ever-changing than previously thought. High-resolution storm photos and data show spinning clouds and turbulent eddies. Storm winds can exceed 400 miles per hour, 644 kilometers per hour, making it one of our solar system's strongest weather events. The Great Red Spot's shape changed, suggesting it may be evolving. This new understanding of the Great Red Spot raised questions about Jupiter's atmosphere and large-scale storms, challenging earlier views. Before the Voyager missions, Jupiter's fourth major moon, Io, was thought to be a frozen, cratered, dead globe like our moon. The scientific community expected its deeply cratered surface to last eons. Voyager's close use of Io were unprecedented. Instead of a dead, cratered environment, Voyager 1 found active volcanoes erupting violently, releasing sulfur and sulfur dioxide hundreds of kilometers into space. As volcanic activity shaped the surface, massive lava flows and sulfur deposits created a unique and multicolored landscape. These volcanic plumes reached altitudes of about 190 miles, 300 kilometers, proving our planet is geologically active. Active volcanism on a non-Earth body was unprecedented. The discovery surprised scientists because they thought distant moons were frozen and inert. We now know that Jupiter's gravitational tug-of-war with Ganymede and Europa causes tidal heating and intense volcanism on Io. Europa was assumed to have an icy surface with craters and impacts like its neighbors. Europa appeared in Voyager images with few impact craters and a bright, smooth surface with black lines and cracks. The surface was younger than expected, indicating active geological processes. Long fissures and no craters showed Europa's frozen crust hid in ocean. Tidal forces from Jupiter's gravity may cause these ice breaks, scientists believe. This may suggest subterranean liquid water heated by tides. This discovery will help the upcoming Europa Clipper mission determine the moon's habitability and search its subsurface ocean for life. The Voyagers established Saturn had a ring system and disproved Jupiter's. Jupiter's massive gravitational field would have fractured or drew in rings. Jupiter's rings, though smaller and weaker than Saturn's, startled Voyager. The rings are mostly dust grains from Jupiter's innermost moons' meteor collisions. The rings were too faint for earthly telescopes to notice, but the Voyager spacecraft's high-resolution equipment did. Ring systems may be more common on huge planets than previously assumed, a momentous discovery. Due to Jupiter's size, scientists expected a strong magnetic field, but they underestimated its strength and breadth. The solar system's largest structure is Jupiter's magnetosphere, which produces a tail that reaches beyond Saturn's orbit and 4 million miles, 6 million kilometers, toward the Sun, according to Voyager data. Jupiter's magnetic field, 14 times greater than Earth's, creates high-energy radiation belts. In this highly magnetic environment, missions that approach Jupiter too near risk radiation damage. Voyager data transformed our understanding of Jupiter's magnetic field and how it interacts with solar winds in space. When Voyager 1 and 2 arrived at Saturn in the early 1980s, scientists wanted to learn about its rings, atmosphere, and moons. However, the two spacecraft's flybys of the ringed giant yielded more comprehensive and dynamic data than expected. Before the Voyagers, scientists expected Saturn's rings would be vast, uniform, and simple. Previously, the rings were thought to be mostly rock and ice from a comet or moon explosion. The Voyager mission revealed that Saturn's rings are more complex and dynamic than previously assumed. One of the most noteworthy results is that the rings are made up of thousands of ringlets and gaps. Voyager revealed previously undiscovered structures, including dark radial patterns around the rings called spokes. These spokes may result from tiny particles interacting with Saturn's magnetic field. Twisted and knotted portions in the braided F-ring suggest interactions with shepherd moons, tiny moon-like bodies inside the rings. The Cassini division, a gap between the A and B rings, had several tiny ringlets. The research demonstrated that Saturn's rings are impacted by its moons and possibly even smaller, unknown moonlets. The Voyager spacecraft revealed the rings' complexity and dynamics to scientists. The atmosphere of Saturn seems more subdued than Jupiter's from Earth, causing many to believe it lacks striking characteristics. Researchers expected cloud bands and tiny atmospheric patterns like those seen in telescopes. Voyager says Saturn's atmosphere is far more dynamic and turbulent than Earth's. The spacecraft observed massive jet streams and winds above 1,100 miles per hour, 1,770 kilometers per hour, faster than those on Earth or Jupiter. Cyclonic systems and huge storms, some Earth-sized, were observed in Saturn's cloud layers. Voyager 2 imaged Saturn's North Pole's hexagonal cloud pattern, a puzzling geometric form that fascinates scientists. Unexpected, the hexagon is still unique in the solar system's atmosphere. Saturn's complex atmosphere revealed that it is a very active planet with unique weather systems driven by internal heat and quick rotation, despite its boring appearance from Earth. Saturn's largest moon, Titan, has fascinated scientists with its rich orange atmosphere. Titan's surface was hidden by this dense cloud cover before Voyager. Its dense, methane-rich atmosphere led to the belief that Titan had liquid hydrocarbon oceans or lakes. At close range, Voyager 1 discovered Titan's thick atmosphere was more challenging than expected. The atmosphere of Titan was nitrogen-rich like Earth's, but it also contained hydrocarbons, complex organic molecules, methane, and others. Deep photochemical haze blanketed the surface, preventing Voyager cameras from taking photographs. However, organic-rich material covering Titan's surface may comprise methane and ethane seas or lakes. After discovering Titan's liquid hydrocarbon lakes, Cassini-Huygens conducted extensive surface research. Voyager found early Earth-like conditions on Titan, raising the potential of prebiotic chemistry or microbiology on the Moon. Saturn's smaller moon, Enceladus, was first assumed to be a lifeless, cold body like many others in the outer solar system. Scientists wanted a barren, cratered terrain. The Voyager probe found geological activity on Enceladus, but could not verify cryovolcanism. Its brilliant, flawless surface suggested Enceladus had been resurfaced lately, possibly internally. In areas of Enceladus with few impact craters, Voyager data showed ongoing resurfacing. Cassini's further observations confirmed that Enceladus is a geologically active planet with water ice geysers erupting from its southern pole. With these geysers and evidence of a subsurface ocean, Enceladus is a top candidate for extrasolar life. Scientists knew Saturn possessed a magnetic field like Jupiter, but they expected it to be weaker and simpler. Voyager 2 found Saturn's magnetosphere very active and powerful. A large magnetosphere full of charged particles is created by the magnetic field, which extends beyond Saturn. Voyager found that Saturn's magnetic field is almost perfectly aligned with its rotational axis, a remarkable and unexplored fact. Saturn's magnetosphere's interaction with its moons, especially Titan, was more intricate than imagined. Titan's atmosphere interacts with Saturn's magnetic field to create a plasma environment. The results demonstrated that Saturn's magnetosphere is a dynamic system impacted by its surroundings and moons, not a miniature Jupiterian analog. Uranus follows. Voyager 2 was the only spacecraft to reach Uranus in January 1986. It discovered 11 additional moons and faint rings around the planet. Voyager 2 discovered Uranus's moons, which were previously considered to be lifeless and frozen. Scientists predicted their highly cratered surfaces will remain unchanged for billions of years. Voyager 2 found that several of Uranus's moons, especially the larger ones, are more geologically complicated than previously imagined. Miranda, Uranus's innermost of 5 largest moons, was one of the solar system's most surprising objects. Its ripples, canyons, and weird patchwork patches suggest dramatic geological occurrences. Massive resurfacing processes probably caused massive cliffs, 12 miles or 20 kilometers tall, and other bizarre geological structures. Some believe Miranda's unique geography was changed during an earlier collision, or that Uranus's tidal forces caused substantial internal activity. 4 of the greatest moons, Ariel, Umbriel, Titania, and Oberon, had rift valleys, canyons, and resurfacing. Ariel's surface was the youngest, lacking impact craters, indicating recent geological activity. Even tiny frozen moons may experience geological activity due to inner heating from tidal interactions, according to the results. Before Voyager 2, Uranus's 98 degrees axial tilt was believed to cause it to rotate nearly sideways. The tilt's effect on Uranus's atmosphere, magnetosphere, and moons was unknown, but scientists expected it to change its seasons. Voyager 2 data shows that Uranus's axial tilt generates extreme seasonal fluctuations. Each pole has 42 years of uninterrupted sunlight, followed by 42 years of darkness. The skewed orientation alters the magnetic field, atmosphere, and rings, creating an asymmetric magnetosphere that interacts differently with the solar wind. Uranus's moons and rings experience tremendous seasonal changes as they circle the planet, which may alter their surface and internal activities. Uranus was unique in the solar system due to its extremely sloped surface, offset magnetic field, and shifting atmosphere. Finally, Neptune. Voyager 2 reached Neptune, the solar system's furthest planet, on August 25, 1989. Voyager 2 finished its amazing tour of the outer planets as it approached this alien world. Since Neptune lies 4.3 billion kilometers, 2.7 billion miles, from the Sun, scientists didn't expect to find many geological or atmospheric features. Like Uranus, they expected a cold, black, featureless world. What Voyager 2 found at Neptune was much more surprising. Scientists expected Neptune's atmosphere would be cold, calm, and featureless like Uranus's due to its great distance from the Sun. This prediction was broken when Voyager 2 found the planet. Since Neptune seems so light blue from Earth, scientists thought it would be dormant with few clouds and no weather. Voyager 2 found extraordinary weather systems on Neptune's dynamic atmosphere. Probe found the Great Dark Spot, a massive storm system like Jupiter's Great Red Spot. A black, oval-shaped storm had 1,500 meters per second winds, the highest in our solar system. Storm was about Earth-sized. Voyager 2 saw the Great Black, a smaller black area, and a fast-moving white cloud named Scooter. The storm's changing clouds showed Neptune's weather's dynamic nature. Astonishingly, scientists discovered that methane clouds at high altitudes throw shadows on lower layers of clouds. These clouds, rather than being powered by the Sun, indicated that Neptune's atmosphere was experiencing strong convection currents. Extreme weather turbulence in Neptune's atmosphere, despite the planet getting only 1/100th of the sunlight that Earth receives, indicates that Neptune has a substantial internal heat source. Its extreme weather is caused by the fact that it radiates 3.66 times more energy than it gets from the Sun. These results were unexpectedly startling because they ran counter to the assumptions of a peaceful, icy universe. Neptune, on the other hand, has storms that are comparable to, if not more so than, any other planet in our solar system. From ground-based investigations, scientists knew that Neptune had faint rings. However, they anticipated that these rings, similar to Uranus's, would be sparse and featureless. The rings of Neptune are significantly more intricate and active than once thought, according to Voyager 2's studies. Although the spacecraft did detect 5 primary rings, They were far darker and dustier than the rings around Jupiter and Saturn. Unusual ring arcs, spotted by Voyager 2, are bright, clumpy sections inside the outermost ring, the Adam's ring. Liberation, equality, and fraternity arcs did not dissipate as predicted. Scientists had assumed that, as a result of gravity, the arcs would spread out uniformly over time. The process of keeping these arcs in place remains a mystery. Galatea, a shepherd moon that orbits just inside the Adam's ring, and maybe others like it, stabilize them, according to scientists. These arcs were unexpectedly found, which raised the possibility that Neptune's ring system is young, brittle, and formed from a moon that was disturbed during its formation. The discovery of these rings further strengthened the argument that the Neptune system is significantly more intricate than previously thought, with processes at work that researchers are still attempting to decipher. Voyager 2. Triton, the largest moon of Neptune, was formerly believed to be a frozen wasteland like many of the other faraway moons in our solar system. A severely cratered surface, according to scientists' expectations, would indicate a geologically dead landscape that is ancient. As it turned out, Triton was one of the solar system's most interesting and dynamic moons. Triton has a thin atmosphere mostly made of nitrogen with trace quantities of methane, according to Voyager 2. With surface pressures lower than 1/170,000 of Earth's atmosphere, the atmosphere is exceedingly thin. Several kilometers into space, the spacecraft found signs of active geysers that were spouting dust and nitrogen gas. This discovery was revolutionary because it proved that Triton, which is incredibly frigid at about -235 degrees Celsius, -391 degrees Fahrenheit, is geologically active. Researchers discovered that Triton has a smooth, youthful surface devoid of impact craters. Surface renewal driven by internal heat sources and evidence of cryovolcanism, ice volcanism, were both observed. Strange, cantaloupe-like terrain and ice cliffs were also photographed by Voyager 2, which could mean that internal forces are continuously shaping Triton's surface. Due to the widespread belief that Triton is a cold, lifeless planet, these findings came as a shock. On the contrary, the moon's surface processes may be influenced by tidal heating as a result of its retrograde orbit around Neptune. As with other gas giants like Jupiter and Saturn, scientists had anticipated that Neptune would have a magnetic field that was roughly parallel to its axis of rotation. Similar to Uranus, Voyager 2 found that Neptune's magnetic field is extremely skewed and off-center. The magnetic field is around 47 degrees off-kilter with respect to Neptune's axis of rotation, and 55% of the planet's radius away from its core. A magnetosphere characterized by chaotic shifting is produced by this peculiar arrangement and interacts with the solar wind in intricate ways. Neptune's slanted and offset magnetic field suggests a deeper fluid layer where superionic water or an uncommon sort of ice may generate its magnetic dynamo, unlike Earth's deep metallic core. These unexpected findings forced scientists to rethink planetary magnetic field theories, especially those for icy giants like Neptune and Uranus. Voyager 2's flyby of Neptune, the last close encounter of the 20th century, changed our picture of the solar system's outer regions. Scientists were astonished by mission data showing that Neptune and Triton are among the most fascinating and dynamic planets in our solar system. Voyagers were moved to study the solar system's farthest regions after their original missions. Our solar system's edge is the massive, active heliosphere. Our solar system is shielded by the solar wind, which deflect a lot of interstellar radiation. At the heliopause, the furthest edge of the heliosphere, the solar wind cannot push against the interstellar medium. Beyond this frontier lies interstellar space, full of substance, radiation, and magnetic fields from distant galaxies. After crossing the heliopause, Voyager 1 entered interstellar space in 2012. After this historic achievement, Voyager 2 sent fresh solar system data in 2018. After the heliopause, the Voyagers discovered several surprising discoveries that challenged our understanding of the boundary between our solar system and the massive interstellar medium. The increased plasma density outside the heliopause was surprising. Scientists predicted that as the spacecraft withdrew from the Sun, particle density would decrease. A plasma density increase immediately beyond the heliopause was confirmed by Voyager 2, launched 2 years later. This surprise discovery suggests interstellar space is not empty. An area with high cosmic ray levels was also found. The heliosphere keeps high-energy particles from reaching Earth. They originate from supernovae and cosmic events. Voyager 1 detected a dramatic rise in cosmic ray power as it approached the heliopause, suggesting that it was approaching the boundary. This cosmic ray wall may help researchers understand the heliosphere's radiation barrier role. Whether interstellar space's magnetic field differs from the Sun's was one of the Voyager's main questions. When the spacecraft approached interstellar space, they observed that the magnetic field was aligned with the solar magnetic field, not changing. Scientists were surprised since they expected a larger difference. It has sparked new solar system galactic interaction hypotheses. Late in 2020, astronomers reported that Voyager 1 had detected a mysterious star humming murmur. Scientists believe interstellar plasma waves provide this feeble, narrowband signal, indicating that space beyond our solar system is not silent. We may learn about plasma behavior in the interstellar medium from this hum. After Voyager 2's passage through the heliopause, it was discovered to be far more turbulent and frothy than expected. Scientists expected a smooth heliopause, but magnetic anomalies, bubbles, and ripples appeared. Scientists are still trying to understand the odd boundary layers generated by trapped particles in the solar wind and interstellar medium, which this turbulence hints is more complicated. The Voyagers have transformed our view of space and beyond, and enthralled audiences worldwide. Each carries a golden record with Earth-related sounds, music, and images to send to any alien culture that may discover them. Despite their declining strength, the Voyagers will likely broadcast data for several years before remaining silent. Even when they cease communicating, they'll silently record our species' insatiable curiosity for billions of years. A heartfelt thank you for being here with us today as we come to the end of our journey at Spaceverse. Your support is what drives our investigation of the cosmos. Remember to hit the notification bell and subscribe to our channel so that you can continue to explore with us. See you until the next time we cross paths in the cosmos.